Okay, so I left you with calculating the main sequence lifetime for the most massive star and the least massive star. So as I mentioned, you can turn the proportionality equation into an actual equation just by putting everything in solar units. So you can put the main sequence lifetime of the sun in here. So you'd have tau of the main sequence for any star divided by tau of the main sequence of the sun equals the mass of the star in relative to the mass of the sun, all to the power minus 2.3. Okay, and then you can just put the numbers in. Okay, so our most massive star is 100 solar masses, so that's going in here, and the lifetime, main sequence lifetime of the sun is 10 to the 10 years. So all you need to do is evaluate that. You get 10 to the 5.4, which is 2 times 10 to the 5 years. So that's 200,000 years. Okay. Now, that might sound like a long time to you, but in astronomical situation, that's a blink of an eye, pretty much. Okay, as we'll see over the course of the module. So basically, massive stars are the ones that live fast, die young, all over in a flash. So that's, you can see that here. Okay. So for the least massive stars, so putting in 0.08 solar masses into this calculation, you get 3 times 10 to the 12 years. Okay, so that's 3,000 billion years. Okay, well, that's actually much older than the universe. Right? So we understand the universe to be about 14 billion years old. This is 3,000 billion years old. So any star with a mass down at this end, has been burning hydrogen ever since it was born and is going to carry on doing so for a very long time. So basically, for these really low mass stars, we've never actually seen them evolve off the main sequence at all. We've never seen them. We've never seen one of these run out of hydrogen yet. There hasn't been enough time in the universe yet. It's actually true for, even if you get down to about 0.8 solar masses, it's still true. Okay. So, so the low mass stars have much, much longer lives on the main sequence. Okay, so I've kind of mentioned this idea a few times already now, so let's do literally a whistle-stop tour of stellar evolution. I mean, there's an entire second-year module on this, stellar structure and evolution. So there's obviously a lot more information that I'm just giving a broad brush overview here in 10 minutes. You can read a little bit more about it in the textbooks, but again, for the purposes of this module, don't get carried away. There's an awful lot of detail in stellar evolution that we just don't need for this module. Pretty much everything you need for this module is here in these notes, and that's always true. Okay, so as I've already mentioned, I think, then once the mass of a star is set, then that determines where on the main sequence it appears and sits there, burning away at its hydrogen at a constant temperature and luminosity for however long, and we've just worked out. But what we're interested in now is what happens when the hydrogen in the core runs out. So the sort of fate of a star, you can divide into sort of two broad categories depending on the mass of the star. So, and this is true in a lot of astronomy, a lot of astrophysics. People talk about low mass stars and high mass stars. So when we're talking about low mass stars, we're basically talking about stars like the sun. Okay, so the sun is a low mass star. It's 1 solar mass. As I say, any star much more mass, much lower mass than the sun, we've never seen evolve anyway, so we don't have to worry about the really low mass ones. So we're talking about, sort of 1 to 10 solar masses here in terms of low mass stars. Okay. And then, so they evolve in one particular way, as we're going to look at in a moment. And then you've got high mass stars, and they are the really big ones, so 10 to 100 times more massive than the sun. They evolve in a different way. And so we can basically split their behavior up into these two broad categories. So let's look at stars like the sun first. So So you've got your hydrogen fusing away in the core, and of course it is steadily turning into helium. So after, like for the sun, after our 10 billion years, then all the hydrogen in that core will have turned into helium, which means you've got no more hydrogen to burn, to fuse. And so the fusion in the core will stop. Okay. Now, as you can imagine, okay, so the fusion in the core is what's keeping the core hot. And once you turn off that energy generation mechanism, the temperature is going to drop to start with, or try to. And if you drop the temperature, then gravity is going to start to win out against the pressure, and the core will shrink. So the core of the star, where the fusion was taking place, this inner 10% of the mass, shrinks. As it shrinks, of course, it will start to heat up again, and it sort of keeps its balance whilst shrinking. Okay, so the pressure-gravity balance, it'll shrink for a while, and start to heat up again. Now, throughout stellar evolution, the envelope, which is what I mean by all the rest of the star that isn't in that core, tends to behave differently and usually oppositely to whatever the core does. I know this is a little bit difficult to understand, but as the core shrinks and will start to heat up, that causes the envelope to expand. Okay? So the outer parts of the star will actually expand. Okay? Now again, thermodynamics, if you think back to thermodynamics, if you've got an expanding gas, it cools down. Okay? If you've ever let the air out of a tire, you know it comes out cold. Okay, so that's a gas that's expanding and cooling as it does so. Same here, you've got a whole star that's expanding, so the surface parts, as they expand, will cool down. So the radius is getting larger and the temperature is dropping. Okay? So that's going to start to change where the star appears on the HI diagram. It's going to get cooler, so therefore it's going to move over to the red side of the HI diagram, but it's also getting larger because the radius is getting bigger. In fact, it's getting a lot bigger. And so even though the temperature drops, the radius expands a lot more, and that means that the luminosity actually goes up. Okay. So that means it becomes a red giant star. Okay. So it will move on the HI diagram from becoming a main sequence star up to the right, to the red side, and up to the giant region. So it becomes a red giant. So the star like the sun will evolve into a red giant. The outer surface will expand. At this point, it's kind of curtains for the Earth because it will expand up to sort of nearly where the Earth's orbit is, 100 times bigger than it is now, and a lot more luminous. But obviously, we've got 5 billion years to work out what to do about that. Get the hell out of here is probably what we need to do. Okay, so again, a detail here that we don't need to worry about too much in this module, but basically that core, which we left sort of shrinking and getting hotter, eventually gets hot enough that helium can fuse. So helium will start to fuse, starts to fuse into sort of things like carbon and nitrogen and oxygen, but basically the whole process repeats. It'll run out of helium at some point quite soon, and the same thing repeats itself. So basically, you still end up with this time an even larger red giant. Now after that, for these low mass stars, they don't have enough mass that when that core contracts for the second time, it will never get hot enough to fuse anything else. It will never get hot enough to sort of burn carbon effectively. So we're now on into the end game, really. And so at some point, we've got this very large sort of red giant type star. You've got a core that's contracting down, basically and getting hotter. Basically, the whole envelope, outer envelope of the star gets ejected. Okay, so it detaches itself and is ejected into space. Not violently, okay, it's basically sort of pushed off, or more like sort of puffed off into space, traveling at like 10 kilometers per second. Again, sounds fast, but again, for astronomy, it's fairly low speed. And so that forms what we will call a planetary nebula. I'll show you a nice picture in a moment. It's nothing to do with planets whatsoever. I'll explain why in a moment. But it goes through this so-called planetary nebula stage. So you get this shell, the whole outer envelope. Basically, half the mass will get ejected into space. The core is still shrinking down. It's never going to burn anything new, but it is shrinking, so it is getting very hot. In fact, they get very, very hot, maybe 100,000 Kelvin. So they start to ionize the surrounding regions, and that lights the whole thing up. So all that gas that was ejected starts to glow, and that's why we get a nebula. Okay, as I'll show you in a moment. The core, which is now really just the remnant of our star, but it's debatable whether you call it a star now because it's not actually fusing very much, or anything. But that will become a white dwarf. Okay? Once it starts to cool down, after it's finished contracting, eventually it gets held up and stabilized at this kind of small size, 0.01 of a solar radius. It will stabilize there, and that becomes a white dwarf, and it just cools. Okay. So that's the words. Let's look at a picture, and a very pretty one it is too. So this is one of our nice Hubble pictures. There's lots of these you can go and look at on the Hubble website. If you look up Planetary Nebula, it's probably worth doing because they are really beautiful. So this glowing gas here is what we would call a planetary nebula. So the reason it's called a planetary nebula is that when they were first discovered with small blurry telescopes with not very good optics, you get a great big colored disk like this, and people thought, oh, we found a new planet. But then they discovered it didn't actually move anywhere, wasn't orbiting around the sun, so the name stuck. It's a nebula. So anything that's called a nebula is basically a source of diffuse light, so not a point like a star, but an extended source of light. So any kind of nebula, it comes from the word nebula. Nebula is basically Latin for fog. Okay, so anything that's nebulous is a bit misty and foggy. Okay, so you've got this big patch of light here, and it's all powered by the hot star left in the middle here. So you can see the star in the middle of this nebula. So that's going to become a white dwarf eventually when it cools down. Okay. And this gas here is slowly expanding into space. You can see these kind of shells here. So that's what I mean. It's a bit like sort of smoke rings being puffed off the upper atmosphere of the star. They're quite unstable, and it just gets heaved off and will just start coasting off into space. Okay. So you've got those nice symmetric shells. Obviously something else funny going on here. You've got some sort of something flying out in this direction as well. So often something breaks the symmetry, whether it's probably little maybe binary companions or something. Who knows? Still an active area of research. Okay, so these are the planetary nebulae. So this is what's going to happen to our sun eventually. Half the mass will be ejected into space, and the rest will end up in the white dwarf in the center. So that's the fate of low mass stars. What happens to the high mass stars? Well, they're kind of similar to start with. Again, the hydrogen in the core will run out, the core will collapse, the envelope expands. You've got a lot more mass this time, so it expands a lot more and becomes one of those supergiant stars at the top of the HR diagram. Okay. So you can see now that we're beginning to explain all the different types of star in the HR diagram. So the red giants and the white dwarfs are explained as evolved stages of low mass stars, and the supergiants are evolved stages of high mass stars. But what happens during this sort of supergiant phase? Well, you've got so much mass in a high mass star that the core can get very hot. Every time the core collapses, you've got so much gravity pulling down, it heats up even more. So you can burn more and more elements, burn straight through carbon, straight through magnesium, straight through silicon, all the way up to iron. Okay? So you end up with a core of pure iron at the last sort of gasp of these high mass stars. But iron is at a very sort of special point. Basically, if you try to fuse two iron nuclei together to get more energy out, you don't. Okay? You don't get any more energy out anymore. So that reaction does not take place. It's not energetically favorable. When you get to elements that are bigger than iron, the only way to get energy out of their nuclei is to split them up with the nuclear fission process, okay, not fuse them together like you do with lighter elements. Okay. So that's why iron occupies a sort of special place in the sort of nuclear physics. You know, that's with fission and nuclear reactors on the Earth, and you're taking heavy nuclei like uranium and splitting them into two lighter nuclei, and you get energy that way. So iron is at the tipping point between fusion and fission. So once you got to iron, your star has nowhere left to go again. It can't burn anything else, and it's kind of game over in a very spectacular way. So in a matter of a few seconds, so things don't usually happen this quickly in astrophysics, but in a matter of a few seconds, the whole core of a star here, could be 10 solar masses of material, collapses, tries to collapse down to a point, and that releases a huge amount of energy, and that basically blows the whole outer layer of the star off as a supernova explosion. Okay. So this is a very violent event. So one of the most violent events we see in astrophysics. So the whole, again, so the same result really, the whole outer layers of the star are blown off into space, but this time the initial explosion was traveling at tens of thousands of kilometers per second, a reasonable fraction of the speed of light actually. So it's very, very spectacular. So again, I don't want to go into details here really, but there can be forces that keep up this remnant star in place. Again, learn more about this in the second year module on stellar structure and evolution, but for now, suffice it to say that you could end up with a very peculiar object that is referred to as a neutron star, which is basically a star that's purely made of neutrons. Okay, and these are very peculiar objects. Quite small and compact, but could have many solar masses of material in them. Okay, so that's the idea of a neutron star. So at the lower end of the high mass stars, like a 10 solar mass star, will end up forming maybe a couple of solar mass neutron stars, something like that. But at the really high mass end, when a 100 solar mass star blows up, even those forces cannot keep the object up. And effectively, we know of no forces at that point currently in physics that would keep an object, collapsing object like that up. And so you end up predicting that you end up with an infinitely small, infinitely dense singularity, which we would refer to as a black hole. Okay, so it's still got a finite mass, but you would assume it just carries on collapsing forever into this sort of infinite, small, infinitely dense thing. There may well be forces there that stabilize it. We don't know. And to be honest, we're never really going to know. And the reason for that is that, as I'm sure you're aware, a key feature of a black hole is now that the gravitational field is so strong that even light itself can't escape. So you have an event horizon inside which light does not escape. Again, as we talked earlier, photons have energy, they have momentum, therefore they're influenced by strong gravitational fields, and you don't get any stronger than this. Okay. We'll come back to black holes later in the module, but this is one way to form a black hole. The way to form a black hole is massive stars exploding and leaving them behind as their remnant object. Okay, so let's have a look at a supernova in action. Okay, so this is a kind of a before and after picture, an optical ground-based picture of the only supernova to explode relatively near to us. It still wasn't actually in our galaxy. It was in a sort of neighboring galaxy of ours. It happened in 1987. Actually, during my PhD, this happened when the world of astronomy got very excited. This was the star, so it was quite a bright star that exploded, as you'd expect from being a massive object, a supergiant star, basically. It exploded. So one night it looked like this. The next night it looked like this. Okay, it became a naked eye object, and it was discovered with the naked eye. Many of these have happened in the historical record. So they were discovered with with the naked eye. Sometimes you can even see them during the day. They're so bright, the ones that have happened in our galaxy. So, these are extremely powerful explosions, and we will come back to them. But for now, it's the end point of the evolution of a massive star. Okay, so that's nicely summarized here on this diagram again from the universe textbook. So here are the starting masses, so anything from 0.1 to 100 solar masses, and stars start life burning hydrogen on the main sequence. But, at some point, either a very long time or a reasonably short time, they run out of hydrogen and start to go down their evolutionary paths. And here you can see this idea of low mass stars evolving one way on the left-hand side and massive stars evolving a different way on the right-hand side. Okay, so the low mass stars going through the red giants, starting to burn helium, basically becoming a red giant again, eventually ejecting their envelopes as Planetary Nebula, so a fairly gentle affair, and leaving behind a white dwarf. Still kind of weird objects, but not as extreme as these things. Okay, and they're typically about half the solar mass. So you might lose half your mass along the way during all of these processes, and especially here. Okay. If you're at the massive end, 10 to 100 solar mass, you'll evolve to a supergiant. Okay, you'll explode as a supernova, and you'll either leave behind a neutron star or a black hole. And here are the masses of the they call them corpse here, a bit of a morbid term, but the stellar remnant, I might like to call them. So yeah, so that's what we need. Okay. So there's a lot of detail hidden in here. Again, don't worry too much about it. The main point here was stellar evolution explains all of those types of stars that we started the lecture with on the HI diagram. Main sequence, red giants, supergiants, white dwarfs. Basically, these things are so faint you can't see them, and these things are temporary. Okay. So stellar evolution explains the main different types of star. That's the key point. And the HI diagram is a way to plot them. Okay. So the HI diagram really acts as what I would call a roadmap for stellar astrophysics. Okay. As soon as you find a new star, new object, stellar object, you'd say, okay, where on the HI diagram is it? Let's find out its spectral type, its temperature. Let's find out its luminosity through the distance. Stick it on the HI diagram. You're going to instantly know roughly what type of star it is. Is it on the main sequence? Has it already evolved off it? We've seen that these main sequence stars, the ones that are burning hydrogen in their cores, the massive ones are much more luminous, the mass-luminosity relation, and they're rarer compared to the lower mass ones. And hopefully you've seen now that the mass of a star determines everything about the future life of a star, pretty much, especially as long as it's a single star, which we'll worry about binaries later. But it determines where on the main sequence it is, how long it spends on that main sequence, where it goes after the main sequence. Does it go red giant, white dwarf, or does it go supergiant, kaboom? And it determines what type of object will be left in its wake at the end, whether it be a white dwarf, a neutron star, or a black hole. Okay, so that's stellar evolution in a nutshell. So let me leave you exploring one of the extreme objects that we've discovered here in this lecture, the white dwarf stars. So you've done this before for the sun in one of the example, one of the MCQ questions, working out the average density of the sun. Here, I'd like you to just have a go at calculating the average density of a white dwarf from its mass and radius. Okay, so a typical white dwarf has about 0.6 of a solar mass. And the key point here is at a radius similar to the Earth. So you can just look up the Earth's radius and assume that the white dwarf has the same radius and work out its average density and see what you come up with this time. Okay, so we'll come back to that answer next time, and we'll go on to look at a special sort of collection of stars called clusters of stars. And that will lead us to an idea of a color magnitude diagram, which is very similar to the HI diagram, but extremely useful at testing all of this kind of theory on stellar evolution that we've just discussed. So we'll see you next time.